Hello judges, we are Team VAMUdeS from Canada. Today we'll demonstrate you how we are ready to fly efficiently and safely.
But first, let's meet our flight team. Hi, my name is Alexandre Guilbeault and I'm a second year electrical engineering student. I'm the GCS operator for the team, so on the flight line my job is going to be to prepare the flight plan, run the pre-flight checklist and monitor the aircraft during the flight.
Hello, my name is Thierry Leclerc. It's my first year in electrical engineering in the University of Sherbrooke. I'm assistant GCS and I'll be in the flight line as assistant GCS and I will cross-check the aircraft performance during the competition.
Hello, I'm Gabriel Bouchard. I am in computer engineering and it's my first year at the University of Sherbrooke. And it's my first year at VAMUdeS too. I'm the team safety pilot. So my main task is to prepare the aircraft on the runway and to assist the competition pilot in operating the aircraft.
My name is Marc-Antoine Lalonde. I study electrical engineering. This is my second year as electrical and software developer. On the flight line, I will be the payload operator and ensure proper operation of the imaging system.
Hello, my name is Cedric Godin. I'm studying electrical engineering. It's my second year on the team. I'm a software developer, but on the flight line I'm the head data analyst. I supervise the processing operation and validate the final results.
Hi, my name is Justin Bruda. This is my first year in computer engineering and this is my first year on the team. In the team I'm mainly software developer and on a flight line I will be data analyst and I will be processing image to identify targets.
My name is Alex. I'm a first year computer engineering student. On the team I'm working on the software of the payload. On the flight line, I'm going to process incoming picture and try to identify targets.
Hi, my name is Yann Lemay-Sévigny. I study in computer engineering since 4 years now. I am with the VAMUdeS team since this time. I am the actual project manager of the team, and this year's on the flight line, I will be the mission coordinator to ensure an efficient mission flow.
Hi, my name is Charles Alexis Carrier. And this is my 4th year on the team. It's also the 4th time I come to this competition. Previously, I was GCS operator. This year, I will be advising the current GCS on the mission flight plan, and I will also be helping him in case any problems arise.
Hi, my name is Valérie Gauthier. I'm a second year electrical engineering student, and this is my second year as a software developer for VAMUdeS. For the competition, I'll be a data analyst on the flight line to process incoming picture used to identify targets.
A short technical overview of our system goes like this. First, the brain of the aircraft, the PIXOC2 autopilot, is connected to several sensors which allow it to navigate smoothly. It is also connected to 2 antennas, one for the safety pilot and one for the telemetry data link. The autopilot also forwards telemetry data to the onboard computer that operates the imagery system. The system also has its own antenna. Every data link on board the aircraft has its own frequency to prevent any interference between them. On the ground control station receives data from the telemetry link and forwards it to the interrupt server. The imagery server receives images from the imaging system and forwards it to the other imagery clients. This data is then processed by our flight team, and the targets are forwarded to the interrupt server. Here is a summary of our planned task and the expected results. As you can see, we're very confident about our autonomous flight takeoff and landing capabilities. Data from our practice flights point towards a 95% results at waypoints navigation. We also expect an 80% result at the airdrop task, as suggests our tests. We gave the sense detect and avoid task a 75% expected result, since we're very confident at being able to avoid stationary obstacles, but less so at avoiding moving obstacles. On the imaging side, we are very experienced at locating and characterizing targets, but have never completed a perfect mission, which is why we gave these tasks an 80% expected results. We will be able to submit an actionable target. We gave the off-axis target task a 70% chance of success, as it is a task that requires a special maneuver on our part, and this is also one that we practice less often. Finally, we will not attempt to submit any target automatically. as it is a very difficult and low rewarding task.
The testing phase of our design starts in mid-December. We have 5 types of tests, which can be represented by this pyramid here. The first level of our test is the ground preparation test, where we test every system on the ground before putting it in the UAS. We then fly our aircraft in manual mode to ensure it's working properly. This is called the RC flight test. Then, we put the autopilot and all of its components into the UAV to test it in flight. This is called the autonomous flight test. Once our autopilot is working properly, we integrate the imagery system into the UAV and we test it in the air. Finally, we go into the advanced features test, such as the airdrop or the SDA. Once all of this is conclusive, we go into mission simulation. Autonomous flight was tested in 49 flights over the last year for a total of more than 9 hours. We also achieved 20 autonomous takeoff and 20 autonomous landing. We had an average of about 5 minutes of manual flying per flight. It was only to ensure that every system was working correctly, and then the UAV would be put back into autonomous mode. To tune the aircraft, we used the R2plane auto-tuning sequence, which did a pretty great job. And for the autonomous takeoff and landing, we analyzed the log data from manual takeoff and landing, and then used the same parameters such as speed and pitch angle into the R2plane auto takeoff and landing sequence. Waypoint accuracy was tested throughout most of our autonomous flight this year. In total, we attempted 205 waypoints and hit all of them with an average error of 16 feet. This is due to the fact that the plane has a maximum climb rate of 2 meters per second or 6.6 feet per second, and this can be a problem if the altitude changes too much between 2 waypoints. Here you can see our last mission simulation where the plane flies very well and hits all of the waypoint. We expect similar result at the competition.
The obstacle avoidance was developed in 3 phases due to the difficulty of the task. The first phase was to establish the best strategy to avoid the obstacles, taking into account the maneuverability of the plane. The second phase was to develop a first Python prototype, which allowed us to establish the feasibility of our strategy. The final phase was to implement our algorithm into Mission Planner, which allows us to perform software-in-the-loop simulations. These simulations were very important as they allowed us to detect certain flaws in our algorithm, such as asking the plane to perform sharper turns than it really could. These sharp turns led to collisions and unpredictable behavior. So we corrected this flaw, and once the software-in-the-loop simulation was top-notch, we went out into the field to perform real-life tests. Real-life tests consisted of 3 15-minute flights against 5 stationary and 3 moving obstacles. 2 of these flights led to 1 collision, and 1 of them led to a 100% avoidance rate. These tests showed us 2 important things. The first one is that avoiding moving obstacles requires a bit of luck. The second one, and the most important, is that our algorithm is safe to use during competition and does not lead to unexpected behavior or crashes. Here is an example of one of our simulations. On the left is an unmodified flight path. As you can see, there is 1 waypoint inside the obstacle and 1 trajectory that passes through the obstacle. On the right is a modified flight path where our algorithm added waypoints around the obstacle so that our aircraft would not fly through it and avoid it properly. 3 types of tests are used to assert the performance of our imaging system. The first type is called ground test. This is where we assert the reliability and performance of our imaging system, and where we make sure that every device that we use works properly. The second type of test is called car test or parking test. This is where we perform the first full integration of our imaging system into the plane, and where we make sure that there are no conflicts between the navigation and imaging system. This is also where we perform synchronization of the various devices, which ensures that we get the best precision as possible. Finally, when the imaging system is ready to fly, we perform flight tests that we mainly use to calibrate our camera to get the best image quality as we can, and to further improve the synchronization of the devices. Our camera is a 24 megapixels DSLR. It provides us with a 25% frontal overlap at 260 feet above ground level. At the same altitude, we have a 0.63 inch per pixel resolution. The overlap ensures that we do not miss any part of the search area during a survey, The resolution is more than enough to identify every target. Our strategy to ensure that we get the best pictures quality as possible is to perform a first flight at 260 feet above ground level. The goal of this first flight is to survey the search area quickly and efficiently to locate every target and identify the vast majority of them. If required, we may then have to perform a flight at 120 feet above ground to get better quality pictures of certain selected targets. During post-processing, we then apply various filters such as brightness and contrast to help the targets stand out from the background. We added this last step since last year we only missed one target, not because we did not have any picture of it, but because it was hidden in the background. We assert localization performance by comparing our results with the ones we obtained through photogrammetry and with the real positions. During the partial mission simulation, we located 12 targets out of 12, with a precision of 11 feet with the raw images and below 3 feet with photogrammetry. We may or may not use this last process during the competition, depending on how well the mission goes, as it is a very time-consuming process.
Air delivery was tested by simply trying to drop the water bottle onto a desired location. Out of the 17 attempts we did, the payload survived 16 times, the other time being due to a human mistake in the installation of the water bottle under the UAV. The average error was about 31.2 feet, which is not as good as we expected. This was mainly due to the effect of the wind and on the bounces that the bottle did once on the ground. We adapted our algorithm to improve our result, and the last drops we did were quite better than the first ones. Here you can see all of the drops we did around the desired location.
The team performed 3 types of full mission test. The first type is a similar mission demonstration during the Unmanned System Canada student competition. This mission includes target geolocalization, autonomous flight, and high-quality imagery. The 2 next types are performed using realistic mission timing and circumstances, including the material and the disposition of the flight crew. So first we begin with ground mission simulation. During this type of simulation, we perform all the action performed on the ground, including the pre-flight preparation, pre-flight checklist, safety briefing, safety-related activities, and then the post-flight processing using former year's pictures as a base data for analysis. The third simulation is the air mission simulation. This type of simulation includes realistic timing, former team members acting as judges, full mission sequence including the pre-flight checklist and safety briefing, a full autonomous flight, search pattern, realistic targets conform to the AUVSI competition specification, and the processing and evaluation using the data gathered during flight. Those tests ensure that we are ready for the real competition and that our process is flawless during flight operations.
Here you can see the results from our last air mission simulation. As you can see, the autonomous flight went quite well as the airdrop. For the object detection, classification and localization, we had our best results so far. Finally, the timeline, we had an 18-minute flight with an 8 minutes of post-processing, which gave us a pretty good score of 65%. In conclusion, we are convinced that our various test phases validate our ability to complete the mission safely and efficiently.
Thank you for your time and see you at the competition.